Welcome back to G-Fun Facts Online. Today we are diving deep into a topic that sits right at the intersection of quantum physics, advanced engineering, and critical medical care. We are going to talk about how we can finally see the invisible wounds of the brain. Imagine a scenario that happens all too often. You are in the dim, sterile light of a trauma bay in a hospital. A physician is looking at a CT scan of a young football player who just took a massive helmet-to-helmet hit. The doctor looks at the scan, and it is pristine. There is no bleeding, no skull fracture, and no bruising. The patient is sent home with a diagnosis of mild concussion and told to rest. But here is the problem. Inside that skull, a microscopic storm is raging. Neural connections have been stretched. Ionic balances are disrupted, and the delicate electrical symphony of the brain has been thrown into chaotic dissonance. Months later, that same player suffers from memory lapses, dizziness, and depression. The scan said he was fine. The physics of his brain said otherwise. This scenario represents the silent epidemic of mild traumatic brain injury. For decades, neurology has been handcuffed by a fundamental limitation. Our best tools, like CT and MRI, are excellent at mapping anatomy. They are great at showing us the hardware of the brain, but they are terrible at mapping function. They cannot hear the software running on that hardware. To hear the brain, to detect the millisecond by millisecond firing of neurons, we have relied on a technology called magnetoencephalography, or MEG. But traditional MEG is a beast. It is a 500-kilogram monolith that requires liquid helium cooling to near absolute zero. It immobilizes the patient in a claustrophobic chamber, and if you move your head even a centimeter, the data is ruined. But that is changing. Enter the Optically Pumped Magnetometer, or OPM. Emerging from the intersection of quantum physics and microfabrication, OPMs are a new class of sensor that is shattering the old paradigms of neuroimaging. These are not room-sized machines. They are the size of a Lego brick. They do not require supercooled liquids. They run at room temperature. And most importantly, they are wearable. In this episode, we are going to delve deep into the world of OPM technology. We will explore how these quantum sensors work, why they are revolutionizing our ability to map brain trauma, and how they are poised to turn the science of the mind into a mobile, accessible clinical reality. To understand why OPMs are so revolutionary, we first have to descend into the quantum realm. The human brain operates on electricity. When a neuron fires, ions flow across its membrane, creating a tiny electric current. According to Ampere's law, every electric current generates a magnetic field. However, the magnetic fields generated by the brain are infinitesimally small. We are talking about femtoteslas, that is 10 to the power of -15 Tesla. For comparison, the Earth's magnetic field is about 50 microteslas. We are trying to hear a whisper in a hurricane. For the last 50 years, the only way to detect these faint signals was using superconducting quantum interference devices, or SQIDs. These relied on quantum tunneling, a phenomenon that only occurs at superconducting temperatures. This necessitated immersing the sensors in a bath of liquid helium at -269 degrees Celsius. This creates two massive problems. First, the standoff problem. Because the sensors must be insulated from the patient's head to prevent frostbite, they are fixed in a rigid helmet with a 2 to 3 centimeter gap between the sensor and the scalp. Since magnetic field strength drops off with the square of the distance, this gap results in a massive loss of signal. Second is the motion problem. If the patient moves their head inside that rigid helmet, the data is useless. This makes scanning children, claustrophobic patients, or anyone with movement disorders nearly impossible. OPMs solve this by ditching the superconductor for a glass cell filled with a hot vapor of alkali atoms, typically rubidium-87, cesium-133, or potassium. These atoms possess a quantum property called spin, which makes them behave like tiny magnetic gyroscopes. The operation of an OPM can be broken down into 3 elegant quantum steps. Step 1 is optical pumping, or polarization. A laser beam, tuned to a specific resonance frequency of the alkali atoms, is shot through the vapor cell. The photons in the laser beam transfer their angular momentum to the atoms, forcing the atomic spins to align in the same direction. The vapor becomes polarized. In this state, the atoms are transparent to the laser light because they can no longer absorb photons. Step 2 is Larmor precession. When a magnetic field like the one from a firing neuron passes through the cell, it exerts a torque on these aligned spins. The atoms begin to wobble or precess around the magnetic field line, much like a spinning top wobbles under gravity. The speed of this wobble is called the Larmor frequency, and it is directly proportional to the strength of the magnetic field. Step 3 is probing, or detection. As the atoms precess, they move out of alignment with the laser. They begin to absorb photons again, reducing the amount of light that passes through the cell. A photodetector on the other side measures this dip in light intensity. By monitoring the modulation of the light, the sensor can calculate the exact strength of the magnetic field. But here is the real magic. To rival the sensitivity of those supercooled squids, OPMs operate in a special state known as the surf regime. That stands for spin exchange relaxation free. In a normal gas, atoms constantly collide, knocking each other's spins out of alignment. This noise limits sensitivity. However, if you heat the gas to increase density and lower the background magnetic field to near zero, a quantum trick occurs. The atoms collide so frequently that the collisions no longer randomize their spins. The spin exchange relaxation is suppressed. The result is that the atoms maintain their coherence for much longer, allowing for incredibly precise measurements of magnetic fields down to 10 to 15 femtoteslas per root hertz. This sensitivity is comparable to, and theoretically better than, the massive superconducting machines of the past. Now, let's look at the engineering. The transition from a 500-kilogram machine to a 500-gram helmet is a paradigm shift. The most critical advantage here is the physics of proximity. Because OPMs operate at room temperature, the sensor can be placed directly on the scalp. The math here is undeniable. Reducing the distance from the brain from 30 millimeters in a squid to just 5 millimeters with an OPM results in a signal magnitude increase of 400 to 500%. Furthermore, this closer proximity allows OPMs to detect finer spatial details. While squids blur the magnetic signals from adjacent brain regions, OPMs can resolve distinct neuronal populations with millimeter precision. However, there is a catch. Remember the surf regime we talked about? It only works if the ambient background magnetic field is effectively zero. The Earth's field is 50,000 nanoteslas, but the surf regime collapses above roughly 20 nanoteslas. To make OPMs work, researchers at institutions like the University of Nottingham and companies like Circa Magnetics have had to develop sophisticated active magnetic shielding. This involves biplanar coils. The subject sits between two large panels containing electromagnetic coils. These coils generate a magnetic field that is exactly equal and opposite to the Earth's field, canceling it out in a specific volume. Additionally, there is onboard nulling. Each OPM sensor contains tiny internal coils that fine-tune the local field to zero. This is the killer app of OPM Meg. It allows the person wearing the helmet to move their head. As they turn, the coils dynamically adjust to keep the sensor in the zero field sweet spot. In a traditional scanner, if a patient sneezes, the data is useless. In an OPM helmet, a patient can nod, drink from a cup, or even play a musical instrument. This opens the door to naturalistic neuroscience, where we can scan brains while they are doing real-world tasks, not just lying frozen in a tube. This brings us to the clinical breakthrough, specifically regarding traumatic brain injury. TBI, particularly concussion, is notoriously difficult to diagnose objectively because it is a functional injury, not a structural one. When brain tissue is injured, the timing of neuronal firing changes. Healthy waking brains are dominated by alpha waves running at 8 to 12 Hz and beta waves at 13 to 30 Hz. Injured brain tissue often shifts to a slower rhythm, generating abnormal delta waves at 1 to 4 Hz and theta waves at 4 to 8 Hz. Traditional SquidMEG has shown that the presence of focal slow-wave activity is a highly accurate predictor of axonal injury. However, squids often miss subtle, deep, or highly focal injuries because of that distance standoff we mentioned earlier. Recent simulations and pilot studies suggest that OPMs, sitting right on the scalp, can detect these pathological slow waves with a significantly higher signal-to-noise ratio. A study by Zahran and colleagues in 2022 demonstrated that OPM arrays could detect signals from deep brain sources with fidelity comparable to whole-head systems, despite using far fewer sensors. At the Queen's Medical Center in Nottingham, the Megabit study has been pioneering the use of OPMs in acute trauma. Their objective is to catch the invisible injury. Many patients with persistent post-concussion symptoms like brain fog and irritability are told it is all in their head because their MRI is normal. OPM-MEG provides objective evidence of the physiological dysfunction. Beyond just hotspots of damage, OPM-MEG maps the functional connectivity of the brain. TBI often involves diffuse axonal injury, which is the shearing of long-range connection fibers. OPMs can measure the lag in communication between different brain areas, revealing a fragmented network that structural imaging simply cannot see. One of the most promising frontiers for this technology is military medicine. Soldiers exposed to blast waves often suffer from blast-induced TBI, which mimics PTSD but has a distinct organic cause. Because OPM systems are lightweight and do not need liquid helium, the UK Ministry of Defence and research partners are exploring mobile MED units. Imagine a Humvee-mounted system that can scan a soldier immediately after an IED blast. This immediate functional triage could prevent the catastrophic second impact syndrome by identifying soldiers who need to be pulled from the line before their brain has healed. Beyond trauma, this technology solves a decades-old problem in pediatrics. Traditional MEG helmets are sized for adults. Put a 5-year-old in one, and their head rattles around, far from the sensors. The signal loss is catastrophic. OPM sensors, however, can be mounted in 3D printed helmets, custom-sized to the patient. For the first time, we can get high-fidelity functional maps of infant and child brains. A landmark study by Ryan Hill and the Nottingham team in 2020 successfully scanned toddlers wearing OPM helmets, measuring brain responses to touch and sound with a clarity that old systems could never achieve in that age group. This is life-changing for conditions like epilepsy. For children with drug-resistant epilepsy, surgery is often the only cure. Success depends on removing the exact piece of tissue causing the seizure. A study by Faze and colleagues in 2024 compared OPM-MEG to SquidMEG in children with epilepsy. The results were stunning. OPMs detected the spikes of epileptic discharge with 2.3 to 4.6 times higher amplitude than skew-wides. Higher amplitude means clearer localization. This allows surgeons to define the resection margin with millimeter accuracy, sparing healthy brain tissue and improving surgical outcomes. So if OPMs are so superior, why aren't they in every hospital yet? The technology is currently in the valley of death between academic breakthrough and commercial ubiquity. The economic landscape plays a major role. A traditional skewed system costs $3 to $4 million, plus $100,000 a year just for the liquid helium. OPM systems eliminate the helium cost, but early prototypes are still expensive due to the custom manufacturing of the vapor cells. However, mass production leveraging semiconductor techniques promises to drive costs down. Key players like Quespin in the USA and Circa Magnetics in the UK are leading this charge. There are technical hurdles too. Current surf OPMs have a bandwidth limit of around 150 Hz. This is fine for most brainwaves, but misses the high-frequency oscillations sometimes used in epilepsy mapping. Researchers are developing new sensor variants to push this limit to 2 kHz. There is also the issue of crosstalk. When you pack 100 magnetometers onto a helmet, the magnetic fields from their internal coils can interfere with one another. And of course, you still need a magnetically shielded room, though these are becoming lighter and cheaper thanks to active shielding. Currently, most systems are sold as research-use-only devices. Gaining FDA and CE approval requires rigorous standardization, data integration with hospital systems, and safety checks for heat dissipation. But despite these hurdles, the trajectory is clear. For centuries, the stethoscope has been the symbol of medicine. It is a simple, non-invasive tool to listen to the rhythm of the heart. Neurology has lacked such a tool. We have had only the autopsy of MRI structure or the imperfect echo of EEG. Optically pumped magnetometry represents the arrival of a true stethoscope for the brain. By harnessing the quantum dance of alkali atoms, we have created a sensor that is sensitive enough to hear the whisper of a neuron, small enough to wear like a hat, and robust enough to work in the real world. For the athlete with a concussion, the soldier with blast injury, and the child with epilepsy, this is not just a physics experiment. It is the promise of being seen, being understood, and finally, being healed. The quantum revolution in neuroscience has begun, and it is wearable. Thanks for listening to G Fun Facts Online.